So this system problem here is trying to be nice. They're both solved for y already. So ideally, all we're doing is setting those equal to each other. Yeah, the 4's even cancel. Add 4 to both sides. Add the 4x to both sides. Factor. So that happens super fast, and that's our 0 and apparently our -4. Then to find those corresponding y values, we can plug them back into either one. I'm going to plug them back into the quadratic just because I don't want to deal with all those negatives. So, but 0 squared minus 4 is -4. So that makes this point 0, -4, which we kind of knew anyway. That was the y-intercept up here. And then for that one, y equals -4 squared minus 4 is what, 16 minus 4, so 12. So that point up there is at -4, 12. Once we do our section on circles, which will be after 9.3, we'll have some fun because then we'll have an equation of a circle and then a parabola going through that circle, and that can hit like as many as 4 times. So we start getting lots of solutions to things. But
is that section in the book? Because I couldn't find it. It just says 1.2.
that is the section on circles.
Okay.
It's back in chapter 1, but all of us actually move it till the end because it's a conics section. So circles, parabolas as conic sections, ellipses, and hyperbolas really are one conversation. And the fact that your text breaks it up into do the circles and then 8 weeks later do all the other conic sections is just kind of weird. So, but yeah, it's not too terribly difficult of a section. The big thing is, it being one of the reasons it's so early is because it relies on completing the square for lots of things. So this weekend might be a nice time to review completing the square.
Oh, joy.
I knew you'd like that.
I just love completing the square. It's so great. Even with all those fractions, fantastic.
Yeah. It's a wonderful opportunity to practice our skills.
I mean that in all the nicest ways.
So hopefully that went okay. Do you guys have any questions on that, though? One of the big things to be careful of is to make sure we kind of keep track of which x goes with which y. So this x generated that y value, this x generated that y value. So those are the ordered pairs or our solutions. We don't want to say something like, x is 0 and -4, while y is, say, 12 and -4. They are in very specific combinations. So our solution should be this ordered pair and that ordered pair. Particularly when we start to get to larger systems, and particularly in Math 112, it comes up a fair amount. We want to make sure we're linking those answers together. Do you guys want a little time to play with that word problem, or you want to dive into it?
Why don't we just dive into it?
So one of the things about this problem, one of the reasons I wanted to make sure that we looked at it, is that we do have to bring something into this problem that's not necessarily explicit to this problem. Anytime we're talking about distances and speeds, so anytime we're talking about rates and distances and time, there's a natural relationship between those that we have to make sure that we're bringing into this problem. The nice thing is it's a relationship that we certainly know, it's just not always one we think of. For example, if I say you go 15 miles per hour for, I don't know, 3 hours, and ask how far did you go, how far would you tell me you went at 15 miles an hour for 3 hours?
45 miles.
Yeah, so you would naturally bring in our relationship that distance equals rate times time, right? Good old DIRT. I like to call it DIRT. Distance is, so I, rate times time, the good old DIRT formula. So that this relationship has to be brought into this question, and any of the questions that talk about rates and times and distances, we kind of want to make sure we consider this relationship. So under that consideration, what are we told happens? We're told we travel upstream at 60 or upstream for 60 miles. So we have a distance upstream of 60 miles. And I'm going to keep the units on them just to keep everything straight. In 3 hours, so that's a time upstream, is 3 hours. And return in 2 hours. So the time, I'm going to say D for downstream, is 2 hours. What is the rate of the boat in still water and the rate of the current? So we're not told a lot here. We're not told, well, we're not explicitly told anyway, the distance downstream. But what is the distance downstream? What does it have to be?
60 miles, because it says they return.
Yeah, it's the same return trip, so it's the same 60 miles. And we're asked what those rates are. So the rate upstream and the rate downstream. Well, the nice thing is we know those rates, right?
Yeah, pretty easy.
Yeah. So we could calculate those rates real quick, but you know, we just divide, right? So 20 miles an hour and 30 miles an hour, right? But it's not what we're asked. So we could, I mean, write those down: 20 miles per hour and 30 miles per hour. What are we asked for? We're asked for the rate of the boat in still water. Neither of these is that rate, right? We're asked for the current in miles per hour, the current of the speed of the water itself in miles per hour. So I want variables for both of those. What do you want to call the rate of the boat in still water?
R.
Well, I've already got so many R's. We could call it R though if you want, but R for rate as opposed to that rate. Yeah, let me use B instead.
I was going to say S subscript W.
I like the B though. The nice thing is you can use anything you want, right?
I mean, still water. It made sense.
Yeah. Still water. You can do that. But the speed of the boat, right? So I'm going to go with B. I like the B. What is the rate of the current? What do you want to use for that?
C.
C for current.
Yep. Look, I'm exceptionally simple.
How about W for water? I'm simpler. No, we can use C. I don't want to be argumentative. So boat and current. So, you know, we have all these distances, rates, and times that the problem either tells us or implies to us, but those aren't the rates and times that we're asked for. The rates that we're asked for are those individual rates. What do we know about the boat speed and the speed of the current? Well, when we travel upstream, what do we know about those?
You're going against the current.
So what do we know about what's going to happen to the B and the C? Is the current going to help the boat or hurt the boat?
Hurt. Well, if you're going upstream, it's going to hinder.
Hinder, yeah.
It would
So-
make B larger.
What's that, Justin?
It would make B larger.
Well, it wouldn't make the B larger. The speed of the boat in still water is the speed of the boat. The boat's not going to go faster or slower. The boat is at a fixed speed.
Oh, my bad.
But it's going to make the overall effect slower, right? But
Right.
notice the speed upstream is slower. It's only 20 miles an hour. Where's that 20 miles an hour come from? It comes from the speed of the boat minus the speed of the current. Because the current is fighting it. That's where that 20 miles an hour comes from. What about the speed downstream? Well, that boat's going the same speed, but what's the current doing this time?
It'd be B plus C, right?
Yeah, it's helping, it's adding, giving us that nice 30 miles per hour, going faster downstream. And that's it. That's our system. It's kind of set up to do addition method nicely. Add those together, you get to B equals 50, so B equals 25 miles per hour. So that's our speed of the boat, or rate of the boat in still water, how fast the boat can go. And if 25 minus C is supposed to equal 20, what's C? Well, it better equal 5. Or if you prefer, if 25 plus C has to be 30, what's C? Same 5. So that's 25, and that's 5. Fair?
Makes sense.
So any questions about that? Those are, ideally moderately straightforward. But yeah, making sure this dirt equation gets kind of into the mix when you're dealing with these rate problems. This one wasn't too bad in that sense, because we just needed to use it to find those rates. When we do like other types of problems, it can be a little bit more involved, but making sure that relationship gets into the problem is helpful. You guys comfortable with that? Okay. So the nice thing about section 9.3 is it's really, technically speaking, not that different. It's just at quite a bit larger of a scale. Well, all at one dimension, technically larger of a scale. So the difference here is that instead of having two equations with two variables that we don't know, x and y, not that they have to be x's and y's, obviously they can be a's and b's and whatnot, we have a system of three equations with three unknowns. In general, if you're going to have a nice, unique solution, you need as many relationships as you have variables. So if there were 4 variables, we'd want 4 relationships. We'd want 4 equations. If there were 5 variables, we'd want 5 equations. Visualizing what this question is asking is a little bit different than visualizing where do lines intersect, because each one of these equations, it's still called linear equations because they're all variables to the first power. But if we were to graph these equations, we'd be graphing them in 3 dimensions, and they would be planes instead of lines. So we'd have one plane, and then the second equation would be a different plane, and those 2 planes would intersect somewhere. So there'd be some line of intersection. Oops, that's terrible. Some line of intersection between those 2 planes. And then the other one, that third plane, would slice through there, and it would intersect those. And that intersection between this line of intersection between the first 2 planes and this line of intersection between the other 2 planes, that point is the solution to the system. So visually, there's a little bit more going on. But if we extend it to, say, 4 variables and 4 equations, we can't even look at that much of the graph, because then we're trying to visualize objects in 4 dimensions instead of 3, and that gets tough. But 4 or 5 or 6 or more variables are actually very common in practical applications. So we do want to make sure we know how to handle larger scale problems. But we're going to stick with 3 for right now. And in this class in total. But the nice thing, well, before I say what the nice thing is, does this, I mean, this is not my best drawing of 3 planes hitting each other, but does this idea make sense that we've got 3 like sheets of paper here, and those 3 sheets of paper, there's a single common point to each of those pieces of paper?
This idea makes so much sense only because I work in SolidWorks. And so when you start a new, like, as soon as you start a new part, it instantly has the 3 planes, top, front, and bottom plane is what they call them in SolidWorks.
Yep.
They're right there on the screen, visually represented.
Yep. And those are all orthogonal to each other. So they all are perpendicular. So, the two intersect there, and then there's the other plane that's perpendicular to those two, right?
Yep.
And those intersect, and they all intersect at that one origin point, right?
Yep.
And that's where this line intersects that line.
Yep. And the thing is, like when you're working in SolidWorks, you have to constantly manipulate which plane you're on for adding other aspects to your part. So like you want to add like a curved handle, then you change the plane, add a drawing onto that plane, center it on the plane, and then attach it to your other part that was maybe on the front plane. So like,
and maybe
the whole
extend
concept,
it up and all,
the whole concept of working on planes is like something. If you worked with SolidWorks at all, you totally know.
Oh yeah. So the nice thing about this idea of visualizing it as the planes intersecting, and like this line of intersecting and that line of intersecting, is actually the process that we use to solve these. If we take two of these equations, that's weird. If we take two of these equations and intersect those two, we will get a line. Then take another two of them, say these two, intersect them, and we'll get a second line. Well, once we have two lines, finding the intersection point between two lines, that's something we can do. That's a 9-1. So that's the plan. Does that seem like a reasonable plan? So I'm going to label these equations just because it's helpful. I'm going to call that 1, 2, and 3. So essentially, we want to take equation 1 and equation 2 and try to solve those simultaneously the same way we did in 9-1. So that's what, 1x minus 4y plus 6z equals negative 14. And 5x minus 8y minus 6z equals 36. Oh, sorry, 38. Now, yesterday, Andrew, you accused me of making a problem rigged so things subtracted nicely. They've clearly done that with this problem as well, right?
I would never.
Never. Yeah, I heard you. So these are set up nicely so we don't have to multiply by anything. But if we did have to, we certainly could. Like if we want to, instead of getting these z's to eliminate, if we want to eliminate those y's, multiply equation 1 by negative 2, and those y's will go away. And we'll look at examples where we have to do a little bit more than what this problem is asking for. But this one, again, is nice that those will cancel. And when we add them together, we get what, 6x minus 12y equals 24. And this now fourth equation, that equation is now an equation of a line. It's in two variables. So we've gone from planes to a line. Well, great. That was our kind of first goal. We essentially built one of these lines of intersection. So then we're going to take two other planes and make the other line of intersection. It doesn't matter which two other planes or which two other equations we grab, just because of how I've labeled this here. I'm going to grab 2 and 3. So it doesn't matter what equations we use as long as it's a different pair than the first one. The key is we have to eliminate the same variable. So if we eliminated z in the first pair, we have to eliminate z in the second pair. If we eliminated y in the first pairing, we have to eliminate y in the second pairing, because we need these two new equations, 4 and 5, to have the same variables in them. If this one's going to be x and y, if equation 4 is going to be x's and y's, we need equation 5 to be x's and y's so we can solve that system. Fair? So you can choose any variable you want, but it's got to be the same choice for both of them. And again, this problem is a little bit rigged. The z's are kind of set up to just work very nicely. And we bring that down, add them together, and we get what, 2x minus what, 24y equals 8 for our equation 5. So now we have 2 lines, and luckily for us, we know how to handle 2 lines. We want to intersect those 2 lines. Those are our tools from yesterday. Now, before doing that, you don't have to do this step, but hopefully it stands out to you guys a bit that there's a 6 in each of those terms, right? So I'm going to divide this whole equation, or both sides of this equation, by 6 to get a smaller relationship. That's just going to be handier to work with. So I'm going to use that as my equation 4 instead. It's the same relationship, just the numbers are smaller. Over here for equation 5, we notice, hey, there's a 2 in each of those. So it's just in our best interests to try to bring the size of those values down if we can, just to make it easier. Again, you don't have to do that, but gosh, it's going to be generally going to make things nicer. And then we can solve the resulting system with whatever tools we want. They both have an 1x, so I'd be tempted to take equation 4 and add it to -1 times equation 5. That would give us x minus 2y equals 4 added to -x plus 12y equals -4. Make sure that -1 multiplies on both sides.
I'm not gonna lie, I did this completely opposite of what you're doing.
Opposite in terms of what, like which ones you picked?
I just multiplied 4 by -2 because
4
it
by
made
-2?
nice. Yeah, equation 4 multiplied by -2, and then you get 12.
Oh, yeah,
and-
yeah,
yeah.
and that's fine as long as, wait, you get 12. You get
Or
the,
no,
they
you get
both
the-
become 24s.
Yeah, the y's cancel out.
Yeah, and it should have worked fine. And the nice thing is you can make those choices, and it should work out just fine. So the x's would cancel there. We would get what, 10y equals 0. That's fun. So we get a y equals 0. Cool. Did not see that coming, but that's okay. Then our x minus 2y is supposed to equal 4. So our x minus 2 times 0 is supposed to equal 4. So when you solved for x, Andrew, did you end up with that 4?
Yeah, so it
Yeah.
came down to -10x equals -40, and
Okay.
then -4 divided by -10 is 4. So
And then when you put that 4 back in, you got the y equals 0, right?
Yep.
So
I just saw the 12 and 24 connection, and I saw
Oh, yeah.
simple math between 12 and 10, and then the
It's-
48 and 8.
yeah, it's hard, to ignore the whole, well, those were nice, but you could also have multiplied, by -3 to make the x's go away.
Yeah, well, and the thing that caught my attention was 24 and 8,
Mm-hmm.
because I know if you multiply them by 2, then you get 48 and 8.
Yep.
And then you get 12 and 2, which would be 10.
Mm-hmm.
So I just saw the
All
the
nice
simple
falling out.
numbers.
Yeah.
Yeah.
And that's, more important than like deciding to factor out the 6 or the 2 is that looking and going, hey, is anything nice? I can make those numbers smaller. That's what I saw that was nice. So did it. You went, oh, wait, I'm seeing these nice relationships with these 10s. Great. You want to look for relationships that might make a choice easier than just grinding through. Now, the trouble is we're not done, right? We have an X value. We have a Y value. What are we missing?
Z.
Missing Z. Do we have any equations that relate X, Y, and Z? Do we have any equations that relate X, Y, and Z?
3 of them.
We got 3 of them. Which one do you want to use? 1, 2, or 3?
1.
1. Can't argue with that. So I'm going to take equation 1 and let X equal 4 and Y equal 0. So that would be 4 minus 4 times 4. Oh, 4 is in this problem. Wait, that would be a 0. So not as many 4s. Plus 6Z equals negative 14. Did I copy that down right? So 4 plus 6Z is equal to negative 14. So 6Z is equal to negative 18. So Z is negative 3. So what did we do? We built one line of intersection. We built the other line of intersection. And then we found where those 2 lines intersect. And where those 2 lines intersect? At 4, 0, negative 3. Excuse me. So again, the nice part of this is that it's really an extension of our elimination method from yesterday, because these will be systems of linear equations, or we'll have like terms each time. So elimination method works nice. You can use substitution on this, but it is a pain just because you get these huge equations when you try to substitute all 3 of them together. It's doable, but it's a pain. Elimination method works nicely, but you can see we're building multiple equations and pulling those equations together. So it's important to have these stay nice and organized. Now, I kind of like this organizational scheme of having, the 3 equations and then say, okay, I'm going to take 2 of those equations to build a 4th, a different 2 of those equations, doesn't matter which 2, to make a 5th. And then those 2 new linear equations together will give me what one of the variables equal. Of course, it could be X, Y, Z. It doesn't matter what they're labeled as, but taking 2 equations, 2 3-variable equations to make 2 2-variable equations, and then taking those 2-variable equations to essentially come up with a 1-variable equation, that's going to be our answer. And then work your way back up. Before we get away from that, I want to have you guys try an example. I don't know why your book likes, that would be good to do.
Trying to find the one that's not rigged, Matt.
You're trying to find one that's a little bit less rigged anyway.
Yeah, we can tell by that. Oh,
Well, it's something I kind of like. It'd be nice for you guys to see that it can sometimes look a little bit different.
No, that's good. I like seeing different. It makes it better because then you have more experience with different ways of doing it.
Oh yeah. But it's always that question like, okay, do we need a nice example, or can we start messing with it a bit? So we want to solve this system if there is a solution. As we talked about yesterday, we could have a line and a parabola, and they might not intersect. In which case, we'll get no answers popping out of this thing. That's okay. Even two lines, they don't always intersect if they're parallel. So it is possible to have three planes that don't all intersect each other. Say, if all those planes were kind of parallel and these intersected at that line, these intersected at that line, these intersected at that line, and they all happen to never touch. Essentially, if you look straight in on this, it would look like that. And all those lines would go, all those planes would go straight back. They might never intersect. That happens sometimes.
It's like a bunch of people living in a city that never meet each other, but they always lived in the same city.
Exactly. It's also possible that two of those that if only two of them are parallel, it's possible that we get one intersection being a nice line, but then when we intersect the third one, it lines up and its intersection is also along the same line. So instead of getting no solutions, that entire line is mapped out twice. We get a infinitely many solutions along that one line. So we do have to be aware that there are other things that we might get. Kind of your default idea is that you'll get a single X, Y, Z triple, as opposed to pair, it's a triple. But other things can happen. Also, with this particular question, and I don't actually know which one we'll get, but also with this question, notice one of the equations doesn't have all three variables in it. Is that okay? Well, it better be okay because we have this problem to do, right? But that just means if we wanted to, we could consider there to be a 0x plus there.
Yeah, I was about to say that.
Yeah. And we're fairly used to that, I think, from our section on polynomials. If it's not there, it's just a zero. Well, a zero coefficient anyway. So if we wanted to follow our pattern, we've got three equations here. Equation 1, 2, and 3. I do like labeling them. Or A, B, and C. Doesn't matter what we label them. I like to change those labels around. Got A, B, and C. And we want to take two of those equations and make equations of lines. But this equation B is already a line. Fair? So if we just take equation B and nothing else, well, we already have one line. So that's nice. Then we can just take A and C, use A and C to make D another line, as long as that's a line. And then we have our two equations much faster. Does that make sense? So essentially this problem, is it rigged? Not really, except that it's already giving us one of the lines because one of the coefficients was zero. And that's actually really common to have happen. So it's not a bad example. Now, if we just added A and C together without doing anything, it's quite possible nothing would cancel and nothing will. So we do have to multiply by something to get stuff to cancel. So what do you want to multiply by either A or C or both to get them to cancel, to get one of the variables to cancel?
-2.
Okay, did we have other choices?
-1.
Or maybe -5, right?
Yeah. I was thinking because the Y's.
Doesn't make us multiply by another number, right? You just like throwing in that negative.
Yeah, you're just changing signs.
Yeah. Is there a reason any one of those choices is either better than the others, or that anything that makes us have to do one of those as opposed to the others?
No.
You can tell, can't you? By my,
I think changing the signs is the easiest,
well, I don't argue that.
in my opinion.
What two variables do we need this line to have?
Y and Z.
Y and Z. So what variable do we have to eliminate?
X.
The X's.
Uh-huh.
Justin, does that make sense? So I totally agree. God, getting rid of those Y's would be so much easier. But then we'd have an equation in Y and Z and another equation in X and Z, and we wouldn't be able to bring those together. And that's what I was saying, kind of a version of what I was saying up here. We can get rid of any variable we want as long as we end up with the same pairing. Here, yeah, it was nice that they gave us essentially an equation, or nice that one of the equations was already aligned, but that did force our hand in what variable we get rid of in the other equation. So we're going to end up multiplying that A by -2 to get a -2x minus 2y minus 2z equals -6, and a 2x plus y plus 5z equals 18. And that wasn't particularly bad on this one, but sometimes it forces us to make like a fairly bad set of conversions or set of manipulations that like we'd really rather not do. And oftentimes not realizing you have to can make people go down kind of bad paths. But this one wasn't bad with a -2. We do end up with a -y plus, 3z equals 12, which isn't too bad. Oh, heck, those y's are even already set up. That's nice. So then if we just take b and d, the y minus 3z equals -11, and the -y plus 3z equals 12, the y's already naturally cancel.
So do the Z's.
Oh no, so do the z's. What does that mean?
I see an issue here.
We get 0 equals what?
1.
1.
Does that mean that there is no solution for this?
Well, technically, it means these three planes intersect when 0 is equal to 1.
I don't think that's a
Is
thing.
never.
Since 0 is never equal to 1, you're right, these never intersect. So we just say no solution. So if we end up with some fundamentally false statement, that means we have that case where the three of them just miss each other. And again, that's going to be common. Sometimes you'll end up instead with a fundamentally true statement. You'll have something that ends up looking like, say, 0 equals 0 or 5 equals 5. When is 5 equal to 5? 5 is always equal to 5. That means that these planes have all intersected at the same line. So for every x value, you've got a point of intersection. For every y value, you have a point of intersection. For every z value, there is a point of intersection. So that line, which is, again, both, either one of these lines, essentially means the lines are the same. So you've got two parallel lines there. The intersection is the equation of the line. And every point along that line is a solution.
So it just means that that line is the same, not that the planes are all parallel too?
The planes have to be parallel for that to happen, but the planes don't have to be on top of each other for that to happen. So like these three planes are all parallel, but they're not all on top of each other, not stacked on each other.
Gotcha.
They're at different angles this way, but they all travel in the same horizontal. Fair? So that line of intersection is our solution. So those are the three things that happen. Either we end up down here with a single solution, something like z equals 5, and then we can go back up and find the others. Or we end up with a fundamentally false statement, which means no solutions. Or we end up with a fundamentally true statement, which means the solution is just one of the lines.
So what do we put for, like, if the solution is one of the lines, how would we answer that? Like, say we came across it in MyOpenMath.
It's x, y, there's a couple of ways to write it, but x, y, z, where y is minus 3z equals negative 11.
Okay. So
it's
just
one way to do it.
I mean, I don't know if we're going to encounter these in MyOpenMath, but
you might. One of the other ways is to parameterize it. So like if these were the same, if that was on 11 instead, we might say, okay, let one of those be a parameter. So let z equal r, so some parameter r. Then that means that y would have to equal negative 11 plus 3r. If we put the r in there, then we have an equation for y in terms of that r. And that's essentially the same thing as this statement. It's just got r's in it instead.
Gotcha.
And then x would be equal to, so that z became an r, that y became negative 11 plus 3r, and then plus the x equals 3. Solve that for x, and you'd have x in terms of r. So that's a parameterized solution. That's the kind of formal solution. But this is essentially the same. It's the set of all x, y, z points where this is true and the x is unconstrained. So it's describing the same line. It just depends on whether you want set builder notation, and I do know how much you like set builder notation, Andrew, or whether you want it parameterized. And parameterized is just fun to say. So
set builder notation's great.
What does your computer want? Ooh, your computer does want parameterized, so that's nice. It specifically says use T instead of R. Okay. Use T. And that's
so we just basically like substituting equations into each other. So
yep.
Pick an exponent, make it equal to T, stick T in for something, solve it equal to Y. Okay.
Yep. So if we wanted to kind of finish that off, we'd have x plus, well, minus 11 plus 3r plus r equals 3. So you'd have x minus 11 plus 4r equals 3. You'd add over the 11. Well, it'd be t's, but it's okay. Yeah, I should make them t's because your book likes t's. T's, s's, and r's are the common, are all commonly used for parameters. So 4t equals 14. And then so x would equal 14 minus 4t. So that would be your other solution, 14 minus 4t.
So where did you? Okay, I'm a little confused. Where did you get the equation for x? I mean, I'm seeing the correlation between the y, but I'm like confused where you got the 3.
Right here. So I picked an equation. You could have used the A or C because they both have an X in them.
Oh, okay. I see what you did.
Let that equal T.
Minus 11 plus 3t for y. I see what you did. Okay. I was a little confused there for a minute. I was like, wait a second. What? Okay, but I get that now.
So those are the 3 possible things that can happen. The parameterization is kind of the worst case scenario, the kind of like whenever you end up with like, it seems weird. It sounds like this, it seems like this should be like the bad result, but this is a great result. You go, this means no, stop, you're done.
I like the 0 = 1 result.
Yeah, just no, done. A single value, okay, you got to back substitute to find the other values, but that's not too bad. It's this solution that makes people cringe. You go, oh, I got to parameterize this, right? It's irritating.
Knowing my open math, I feel like that's the one that they're going to pick often.
Well, it should be that at least one of them occurs each time, right? And there are only like 8 different questions in that section, so.
Long as the whole section.
So there are a couple word problems in there. I wanted to talk a little bit about word problems, but we are way over time. Well, not way over time, 10 minutes over time. So I'm going to have to send you guys to go play with those. But essentially, the word problems from here are just like the word problems from the other section, the 9-1, except that they've got 3 equations instead of just 2. So just to glance at one before I send you guys off, they do tend to be a little intimidating because there's a lot of information in them. But we receive a gift of so much money. So we're going to have a total money equation. So we got to figure out what that equation is. The money's invested in stocks, bonds, and CDs. They made, they made this much money, so we'll have an interest equation. And that interest equation should end up being equal to the 7,085. The total money equation should end up being 185,000. And then we should be told something else. Oh, well, we invest $10,000 more in bonds than CDs. So we will have a bonds versus CDs equation. And if we, like, say, subtracted them, we would get the 10,000. So that's probably going to end up being equal to 10,000, depending on how we write that equation. Those are the 3 relationships that the problem talks about. Each one of those relationships will be an equation.
So for like that first one right there, that would just be like CD plus bonds plus what, like stocks equals the total, right? C plus B plus S.
Yep.
And the second one would be like, so C times the percentage rate for each one equals 7,000
for each one,
effectively. Yeah.
Yep.
Yeah.
Plus S and 10.3. Well, in percent notation.
Yeah.
Equals the 7,085.
What bonds minus B minus C equals 10,000? That's your equation.
More in bonds, so bonds is bigger, right? So B minus C equals 10 grand. And that's it. That's the system.
Gotcha.
So when you're reading these word problems, particularly when we're looking for a system of equations, almost each equation should be kind of its own sentence. You know, what things are we talking about here? We're talking about how much money, how much interest, and this relationship between the two. Okay, so I should have an equation for each of those. Fair? All right. So go play with these. If you have any questions along the way, let me know. I think that homework assignment is listed as due Friday. Is that right? So we won't be able to talk before. No. That's due Monday. Oh, okay, cool. Okay, I was worried. The 9/1 is due Friday. So we're all kinds of good. You guys can play with that, and then we can talk about those word problems if we need to on Monday after you guys played with them. Don't put that off. Playing with them before we talk about them is helpful. Okay.
Alrighty.
All right. Let me know if you need anything. Other than that, have a wonderful day.